Gravity doesn't have hands. It can't push, can't sculpt, can't build. Yet somehow it carved Saturn's rings with clockwork precision. Squeezed Io, a moon smaller than ours, into a volcanic hellscape with hundreds of eruptions. And shaped every sphere you've ever seen in space from nothing but chaos. It's the universe's invisible artist. It never touches anything, never exerts direct force, just bends space. And space tells matter how to move. This is the force that shaped everything. Look at Jupiter, a perfect sphere. Well, almost. It's slightly flattened at the poles because it spins so fast. Now look at asteroid Gaspra, shaped like a potato, lumpy, irregular, clearly not round. Same solar system, same physics, same gravity. So why are big things round and small things not? The answer isn't big things are just bigger. That's circular reasoning. The answer is about a battle, a cosmic tug-of-war between two forces. On one side, chemical bonds, the electromagnetic force holding atoms together. It's what makes rocks solid, what lets mountains stand tall, what gives asteroids their strength to resist being crushed. On the other side, gravity. Weak at human scales, you can jump, but relentless. And it scales with mass. The bigger an object gets, the more mass it has. The more mass, the stronger gravity pulls everything toward the center. From all directions, equally. And when gravity wins, when it gets strong enough to overcome the strength of rock itself, something beautiful happens. The object collapses into the only shape where every point on the surface is equally distant from the center. A sphere. But here's the precise question. At what size does gravity win? The answer depends on what you're made of. For icy objects, made of frozen water, methane, ammonia, the threshold is around 400 kilometers in diameter. Saturn's moon Mimas, 396 kilometers across. Barely makes the cut. It's the smallest known object in hydrostatic equilibrium, the technical term for pulled into a sphere by its own gravity. Ice is soft. It deforms easily. So gravity doesn't need to be as strong to squash it into shape. For rocky objects, silicates, iron, denser materials, you need 600 kilometers or more. Vesta, 525 kilometers, made of rock, not round. Close, but the chemical bonds holding it together are still strong enough to resist full sphericity. Ceres, 940 kilometers, also rocky, perfectly round. The crossover happens somewhere between 500 and 900 kilometers for rocky bodies. Below that, chemistry wins, irregular shapes. Above that, gravity wins, spheres. When a planet forms, it doesn't start round, it starts as a clump, a gravitational aggregate of smaller pieces, rocks, ice, debris, all stuck together by weak gravity and collisions. But as it grows, as more material falls onto it, the pressure at the center increases. Eventually, that pressure exceeds the strength of the material itself. The rock flows like a liquid. Not quickly, this takes millions of years, but it flows. Material from the high points, mountains, irregularities, gets pulled down by gravity. It fills in the low points, valleys, depressions. The process continues until every point on the surface is at the same gravitational potential, a sphere. Scientists call this hydrostatic equilibrium, the shape where gravity and pressure balance perfectly. But there's a twist. If the object spins, centrifugal force at the equator pushes outward, creating a bulge. Saturn spins once every 10.7 hours. That's fast. Really fast for something so massive. Result? It's 10% wider at the equator than pole to pole, an oblate spheroid. Earth spins once every 24 hours, slower, so it's only 0.3% wider at the equator. Gravity pulls everything into spheres. Rotation flattens them, and the faster they spin, the more flattened they become. This is how the invisible architect works, patiently, relentlessly, shaping worlds from the inside out. Saturn's rings. One of the most beautiful structures in the solar system, spanning 282,000 kilometers from the planet, yet only about 10 meters thick in most places. From Earth, they look like smooth bands, but up close, thousands of separate ringlets, gaps, waves, structure upon structure upon structure. For centuries, astronomers asked, why does Saturn have rings? Wrong question. The right question is, why do Saturn's rings exist exactly where they do? 1848. French astronomer Edouard Roche sits down with Newton's equations and asks a question. How close can a moon get to a planet before the planet's gravity tears it apart? The answer isn't obvious. You might think, gravity pulls the moon toward the planet, so the moon just falls in. But that's not what happens. Gravity isn't uniform across the moon. The near side, closer to Saturn, feels stronger pull than the far side. This creates a tidal force, a stretching force. If the moon is far enough away, its own gravity holds it together. The tidal force is annoying but manageable. But as it gets closer, the tidal force increases, faster than the moon's self-gravity. At a certain distance, the Roche limit, the tidal force exceeds the moon's self-gravity. The moon comes apart. Not explosively, gently. It just stops being able to hold itself together. The pieces spread out into an orbit, a ring. Roche calculated the exact distance. D equals 2.44 times R times the density of the planet, divided by the density of the moon to the 1/3 power, where R is the planet's radius and the rhos are densities. For Saturn, about 137,000 kilometers from the center. And where do Saturn's rings live? Between 67,000 and 137,000 kilometers from Saturn's center. Exactly inside the Roche limit. Every single particle. For decades, scientists debated, are Saturn's rings ancient, billions of years old, or young, just hundreds of millions? Data from NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, answered it. Young. Probably only 100 to 400 million years old. The dinosaurs were already walking Earth when Saturn's rings formed. But how? 2023 research from NASA and Durham University proposes this. 2 icy moons were orbiting Saturn. Large ones, maybe the size of Mimas or Enceladus. Their orbits were stable for billions of years. But the sun's gravity, tiny but persistent, slowly nudged them. A gravitational resonance built up over millions of years. Their orbits elongated, tilted. Eventually, they collided. At over 10,000 kilometers per second, the impact shattered both moons into billions of pieces. Most of the debris, rock and ice, flew outward, beyond the Roche limit. That material coalesced. It became some of Saturn's current moons. But some debris, the lightest, iciest pieces, fell inward, inside the Roche limit. There, Saturn's gravity prevented them from clumping back together. They spread out, flattened, organized themselves into rings through countless collisions. And because the collisions stripped away the rocky cores first, denser material fell onto Saturn. What remained in the rings is almost pure ice. 99% water ice. That's why they're so bright, so reflective. The Roche limit doesn't just explain where rings exist. It explains why they're made of ice, why they're so thin, why they're temporary, slowly falling into Saturn as we speak. Gravity set the boundary, collisions filled it, and the rings are the result. Gravity's most delicate sculpture. Io, Jupiter's innermost large moon. Slightly bigger than Earth's moon, but nothing like it. Io has over 400 active volcanoes, more volcanic activity than every other world in the solar system combined. Lava lakes, sulfur geysers erupting 300 kilometers into space, surface temperatures exceeding 1,800 Kelvin. And it's not slowing down. Io is the most volcanically active object we've ever discovered. But here's the mystery. Io is tiny. It should have cooled off billions of years ago. Its interior should be solid, dead, cold. Instead, it's hell. Why? The answer is gravity. But not Jupiter's gravity pulling Io inward. It's gravity squeezing Io. Over and over, billions of times. Io orbits Jupiter once every 42.5 hours. But it's not a circular orbit. It's slightly elliptical, eccentric. That means sometimes Io is closer to Jupiter, sometimes farther. When Io is close, Jupiter's gravity creates a tidal bulge, pulling Io into an elongated shape. When Io is far, that bulge relaxes. Close, stretch. Far, relax. Close, stretch. Far, relax. Billions of cycles. Every squeeze generates friction inside Io. The rock bends, cracks, grinds against itself. That friction converts gravitational potential energy into heat. A lot of heat. Io generates about 2.5 watts per square meter of internal heat, 60 times more than Earth. That's enough to keep the interior molten, to drive convection, to push magma to the surface, to create hell. But wait, if tidal heating requires an eccentric orbit, and orbits naturally circularize over time due to tidal friction, shouldn't Io's orbit have become circular billions of years ago? Yes, it should have. So why hasn't it? The answer: orbital resonance. Io isn't alone. Europa orbits farther out, Ganymede beyond that, and their orbits are locked in a mathematical relationship. For every one orbit Io makes, Europa makes exactly 2, and Ganymede makes exactly 4. This means every time Io passes Europa, Europa is in almost the same position. Europa's gravity tugs on Io, slightly. Over millions of years, these tugs add up. They keep pumping Io's orbit back into eccentricity, preventing it from circularizing. Europa and Ganymede are stealing orbital energy from Io and preventing tidal dissipation from damping out the eccentricity. Without Europa and Ganymede, Io would be geologically dead. With them, volcanic hell. Forever. (2024) NASA's Juno spacecraft makes 2 close flybys of Io, the closest in decades, and discovers something strange. Io's volcanoes aren't evenly distributed. There are volcanoes at the poles, surprisingly many, but they're less energetic than equatorial volcanoes. This matches 2024 research published in Nature. Io does not have a global magma ocean. Previous models predicted a shallow, planet-wide magma ocean just below the crust. That would create uniform volcanism. But Juno's gravity measurements show Io's interior is mostly solid, with a partially molten asthenosphere, a layer of squishy, partially melted rock about 50 to 100 kilometers below the surface. The tidal heating happens primarily in that layer. Not evenly, more at the equator, where tidal stresses are strongest. Magma finds weaknesses in the lithosphere and erupts wherever it can break through. Hence volcanoes at poles too, just less powerful. Io isn't a ball of liquid rock with a thin crust. It's a solid moon with a squeezed, partially molten layer being constantly kneaded by Jupiter's gravity. Gravity doesn't melt Io by heating it directly. Gravity makes Io melt itself through friction, over and over, forever. 2 objects in space, like the Sun and Earth, orbit each other predictably. We've understood that since Newton. But add a 3rd object, say a spacecraft, and the math becomes chaos. In 1772, mathematician Joseph Louis Lagrange asked, "Are there any points in space where a small object can orbit with 2 larger objects and remain in a fixed position relative to them?" He found 5 spots where the gravitational pull of both large objects and the centrifugal force of orbital motion perfectly balance. We call them Lagrange points. And they're not theoretical curiosities. They're real. We've been using them for decades. L1, between the Sun and Earth. About 1.5 million kilometers from Earth toward the Sun. Perfect for solar observatories. Constant view of the Sun without Earth blocking it. SOHO, Discover, and WIM spacecraft all sit here. L2, 1.5 million kilometers from Earth, away from the Sun. Perfect for deep space telescopes, always in Earth's shadow, protected from sunlight. This is where the James Webb Space Telescope lives. Launched December 2021, arrived at L2 in January 2022. It doesn't sit exactly at L2, that's unstable, but orbits around it in a halo orbit, completing 1 loop every 168 days. L3, on the opposite side of the Sun from Earth. Almost never used, too far, too difficult to communicate with. L4 and L5. These are special. They sit 60 degrees ahead of and behind Earth in its orbit, forming equilateral triangles with the Sun and Earth. Unlike L1, L2, and L3, which are unstable and require constant adjustments, L4 and L5 are naturally stable. Objects there don't drift away. They're trapped in gravitational valleys. Earth has at least 1 asteroid at L4, 2010 TK7. Mars has several. Jupiter has thousands. We call them Trojan asteroids. Lagrange points are gravitational parking spots. They let spacecraft orbit the Sun at the same rate as Earth without using fuel. They stay in fixed positions relative to us. Easy communication, constant sunlight conditions. James Webb, Euclid, Gaia, WMAP, Planck, all at L2, and more are coming. The Nancy Grace Roman Space Telescope, ESA's Plato and Ariel, Japan's Lightbird, all headed to L2. These points exist between every pair of gravitationally bound objects. Earth and Moon have Lagrange points, where we're planning to put future space stations. Jupiter and its moons have them. Trojans orbit at Jupiter, Sun, L4 and L5. Every star with a planet has them. Every planet with a moon. Lagrange solved the three-body problem in 1772. And 250 years later, we're still using his solution to park telescopes in space. Gravity doesn't just pull objects together or tear them apart. It creates invisible architecture, stable points, parking spots, structure in empty space. You can't see it, but it's there. And we're building our future on it. Gravity shapes worlds without touching them. It pulls asteroids into spheres once they cross a threshold. 400 kilometers for ice, 600 kilometers for rock. It defines the Roche limit, drawing a line in space inside which no moon can survive. Only rings can exist. It squeezes Io billions of times, converting orbital energy into volcanic hell. It creates Lagrange points, invisible but real places where spacecraft can park for decades. Every sphere you see, gravity. Every ring system, gravity. Every tidally locked moon, gravity. Every stable orbit, gravity. It's the weakest of the four fundamental forces, but it's the only one that scales without limit. Add more mass, gravity gets stronger, always. And given enough mass, gravity always wins. What we see in our solar system isn't unique. Every planetary system has a Roche limit. Every gas giant likely has rings, or had them in the past. Every system with moons in resonance generates tidal heating. Every star with a planet creates 5 Lagrange points. And on larger scales, gravity sculpts everything. Spiral arms of galaxies, clusters of galaxies, the cosmic web itself, filaments of dark matter connecting superclusters across billions of light years. All of it shaped by the same force. A force that never touches anything, just bends space and waits for matter to respond. Gravity is patient. Gravity is precise. And gravity never stops sculpting. Every structure you've ever seen in space was built without hands. Spheres pulled from chaos. Rings carved at precise distances. Moons squeezed into furnaces. Parking spots etched into empty space. Gravity doesn't care about plans or blueprints. It follows one rule. Mass tells space how to bend, and space tells matter how to move. That's it. But look what that simple rule creates. Hell, beauty, order, chaos, everything. But here's what still doesn't make sense. Mars has been dead for billions of years. Its core is frozen. No plate tectonics. No volcanic activity. So why is Olympus Mons, the largest volcano in the solar system, twice the height of Everest, sitting on its surface? And why is tiny Enceladus, a frozen moon that should be geologically dead, erupting geysers of water into space right now? Gravity shapes worlds, but something else keeps them burning. This is Cosmic Canvas, where we reveal the invisible forces shaping reality. Until next time, remember that everything you see was built by something you can't. Gravity shapes worlds without ever touching them.